see you. Let us recall our previous discussion. So that was electric power, or electric current. Who will remind me how we determine electric power delivered, or let's say dissipated on a resistor?
Product of I square and L.
So I stands for current, and R stands for electrical resistance. So we also introduced specific electrical resistance as a parameter which defines properties of the material from which the resistor is made, and considered also microscopic, the kinetic nature of charge transfer. So in this case, we consider charge carriers, which are most commonly electrons considered in metals, as some free charge carriers which can move in the bulk of the conductor and interact with the crystal lattice of the conductor. So once we create some internal electric field inside such a conductor, electric force accelerates charge carriers in the direction of electric field or in opposite direction, depends on the sign, but if electrons are negatively charged, and obviously it will get some acceleration. So acceleration will be constant if electric force and electric field is constant, and we will consider like charge carriers moving along a straight line with constant acceleration. So that is true until they interact with the crystal lattice and lose this gain energy because of scattering from this crystal lattice. So that's why we consider the time of flight, like time of free flight of electrons between two successive interaction scattering acts with the crystalline lattice. And during this time, we determine what will be the acceleration and some net drift velocity in the direction of electric field. So that is very important to distinguish between electric field induced drift velocity, which is the same for all charges which can move in the conductor, and also with thermal velocity. Thermal velocity is just thermodynamic feature. All these charge carriers which can move, they are moving in random directions. So that's why thermal velocity vectors are randomly oriented. They are different. There is distribution for thermal velocities depending on temperature. So it's a function of temperature. And obviously, the average thermal velocity will be equal to zero because we have many charge carriers. They have randomly oriented thermal velocity vectors, and average will be equal to zero. If we consider average of drift velocity, it will be the same drift velocity because they all will be in the same direction and with the same magnet. So this need to keep in mind. And today we introduce already this DC, so-called direct current electric circuits. So what is direct current? Any definition of direct current you can suggest?
Current is constant flow.
Here we need to specify that it doesn't change the direction. So it's constant flow in the same direction. However, the key here is the same direction because the flow may be not constant. So it may change in magnitude, which is a specific case. Hopefully we will have some time to discuss it. It's so-called RC, resistor capacitor electric circuit, when we have time-dependent magnitude of electric current. But it will remain flowing in the same direction during certain time. And in this case, it still will be direct current, still it changes in magnitude, but its direction is the same. So that is the type of electric circuits which we're going to discuss today and also in the near future. Later, we will shift to alternating current, which in this case, electric current will change the direction. It will both change magnitude and direction. So that is alternating current. So let us consider a simple electric circuit. We have some battery. And some electrical resistor. So battery will be denoted here as E, here small r, here capital R. And let's say this is our electric current which flows through this electric circuit. So these are the components. So it's of course the most primitive, but complete example of DC electric circuit. So what do we have here? We have a battery which produces certain internal voltage. It's established in the literature, calls this internal voltage as electromotive force, EMF. So you will see this quite often in different textbooks. So this is internal potential difference between terminals of the battery and which defines by the nature of some chemical processes, let's say if we're talking about some chemical battery, which are embedded in this battery. So it depends on the design and materials we pick up. Each battery may possess different electromotive force. But that is defined by the properties of the battery, and that's the maximum potential difference at the terminals of the battery. However, when we have a battery connected to electric circuit, we don't get at terminals of the battery this internal internal potential difference, which is called EMF. It will be a little bit smaller, depends on the quality of the battery, and also depends on the magnitude of electric current, because the deviation of actual potential difference at the terminal of the battery will be, like from this electromotive force, will be proportional to the magnitude of electric current, which is flowing through the electric circuit. So now the question is, any suggestions, what is the reason for this deviation? Why we don't get this EMF value at terminals in battery connected to the electric circuit, but we get a little bit lower potential difference?
It's got its own internal resistance.
It possesses some internal resistance. What is the origin of this internal resistance? Cannot we get rid of it? Can we make an ideal battery which will not have any internal resistance? No, and why?
Well, because it doesn't make a kind of work like thermal work, it heats up a little bit.
Well, it heats up because of
This is
internal resistance. So we know already that when there is a current, the dissipation of heat over a resistor will be I squared times magnitude of resistance. So Obviously, we want this to be as small as possible, not only because of deviation of potential difference at the electrodes of the battery, but also another reason we don't want to overheat this battery, and that the overheating increase of temperature could have some bad influences on the performance of this or increases the degradation. So obviously we cannot make it equal to zero because every battery is made of some materials. These materials stand in front of charge carriers which have to go through this battery. So while a charge carrier is going through the battery, it gains some potential energy, means this battery as a system performs some work on these charge carriers and increases its potential energy. However, during this process, it still has to go through the battery. It goes through the material of the battery. It interacts with scatters on the crystalline lattice of these materials of the battery and dissipates some part of its energy. And that will be proportional to this internal resistance of the battery. So taking this into account, we can consider in more details how potential is changing for charge carriers which are floating through this DC electric circuit. So two axes. So this will be, let's say, our potential. Here we will kind of open this electric circuit. So it will be the battery with internal resistance. And here will be the load resistor. So this is E, here's R, and here is capital R. So in order to show schematically the real battery, we show kind of ideal battery with electromotive force E, and then attach some series resistance to it. So how shown here. Now, if we consider some point, let's say point A here, it's the beginning of the electric circuit, and its end because it's closed. So from this point A, at which we may consider potential equal to zero, it reaches to maximum value equal to electromotive force E as charge carrier moves through the battery. So the ideal part of the battery. But then there is non-ideal part of the battery, and that is internal resistance. So when it reaches to the, so it stays constant. When it reaches to the internal resistance, it's the potential drops, and here this new potential will be I times R, capital R. So that will be voltage drop over the load resistor. And then if we consider already like passing through the load resistor, potential should drop to zero. So if we consider here point B, which point A and point B, they coincide when we close the circuit. So here, potential will be the same. It will be potential zero. We just consider this potential at this given point as zero, and with respect to this zero potential, we show all other potentials. So now, if we want to determine potential difference, or voltage drop over this load resistor, delta V, let's call it, that will be electromotive force of the battery minus magnitude of electric current which flows through this DC electric circuit times, this small r, internal resistance of the battery. So from here, if we want to determine magnitude of electric current, that will be epsilon, which is electromotive force, divided by the total resistance of the circuit. It will be internal resistance plus load resistance. So now let us record how we determine electric power which dissipates on the load resistance. So that is P equals to I squared times R. And here we will substitute our previous equation. So it will be epsilon squared divided by R plus capital R plus R in second power times capital R. So that is the power which will be dissipated over this load resistor. And quite common question is what magnitude of this resistor, load resistor, should be in order to dissipate maximum possible power under given conditions when electromotive force is given and internal resistance of this battery is also given. So we want to know what value of the load resistor we need to attach to such battery in order to get the maximum possible power delivered to this load resistor. So any suggestions how we answer this question? If we have some function and we want to find the value of independent variable at which function reaches its maximum value, how we approach this task?
Find derivative.
Exactly. We take first derivative of the function over this independent variable and set it to 0, because at the maximum point the change of the function will be like derivative of the function will be equal to 0. Taking into account this condition, we can manage to determine the maximum, the magnitude of the independent variable when the function reaches the maximum. So here we have a function. So this is our function is power as a function of load resistance. So what we need to do, we need to take first derivative of this function over load resistor and set it to 0. So let us try to do it. How? Okay, first derivative of power over resistance. Of our function, and here we have epsilon square over R capital plus R square, and here we have also R capital. So in order to make it easier for us, let us rearrange it a little bit. So we will have d over dr, and here in parentheses we will have epsilon squared times capital R times R plus capital R plus R in second minus second power, and that we set to 0. So what will be this derivative? It's actually derivative of two functions. So we have one function here and function here. So it's a product of two functions. And here we have epsilon square times R, capital R plus R in minus second power. And then we have plus epsilon square R times minus 2 times capital R plus R in minus third power. And that we set to 0. So now, in order to make it similar, the left and right, like first and second term in this equation, let us multiply and divide the first term, this one, by capital R plus R. So that will be epsilon square times R plus capital R plus R divided by capital R plus R in third power. Then we take into account this minus, so it will be minus 2 epsilon square times R divided by capital R plus R in third power. So this will be equal, so we have the same denominators. This will be equal to epsilon square R minus capital R divided by capital R plus R in the third power. So now we set this equal to 0, and under which condition this equation will be equal to 0?
When our inner
Load resistance. So we look at the, in these cases, we don't care about denominator, we care only about numerator. So here, electromotive force obviously will not be equal to 0, because if it's equal to 0, then there's no electric circuit. And that's why this, in this parenthesis, we should have 0, means that they should be equal to each other. So if electromotive force and internal resistance are given, then the maximum value, so the value of load resistor, its magnitude, will be necessary to set equal to the internal resistance of the battery in order to dissipate maximum energy, like electric energy, over this load resistor. So R, let's call maximum, will be equal to internal resistance of the battery. So this should remember. That's kind of special condition when we have maximum dissipation of energy over load resistance. So now we need to consider some theory of electric circuits, and we start from connection of different resistors in series and in parallel. So obviously, in similarity with capacitors, we can create so-called battery, either of capacitors or of resistors. There are two options to connect resistors, and they are in series or in parallel. So let us consider first in series. We have two resistors which are connected in series, and we have some battery. That's plus minus. We have at terminals of this battery some potential difference delta V, and here we have electric current I flowing through this circuit, where this is R1 and this is R2. So there will be some voltage drop over each of this resistor, depending on its magnitude. So this will be delta V1 and this will be delta V2. So what can we tell about currents I1 and I2, which are flowing through resistor R1 and R2? Are they the same or they are different? They are the same because there are no options for electric current to flow other direction. They connected in series. So that's why we can write that I1 plus I sorry, no, I1 is equal to I2, and that is equal to I, electric current. Now, what we can tell about potential difference delta V over the terminals of the battery, that will consist of two terms, voltage drop over first and second resistor. So delta V1 plus delta V2. So in this case, we can express this voltage drop delta V as current I times some R equivalent of the electric circuit, where we have two resistors connected in series. So we can write that I times R equivalent is equal to I times R1 plus I times R2. We factor out this I, so we can cancel it out. And from here, we see that R equivalent is equal to R1 plus R2, or whatever number of resistors which are connected in series. So that is the way how we determine equivalent resistance of resistors connected in series. Let us consider another example when we have two resistors connected in parallel. So we have one resistor, another resistor, we have a battery. Again, plus minus delta V. Here we have some electric current I. So this is R1, this is R2. Here will be some current I1, here current I2, and in this case, when we have parallel connection, the total current I, which flows through the battery, will split in two components. That will be I1 plus I2. However, the potential difference between terminals of the battery and terminals of the resistors will be the same since they are connected in parallel. So delta V will be equal to delta V1, and that will be equal to delta V2. So how we can express electric current? According to Ohm's law, electric current, that is delta V divided by R equivalent. So for whole circuit, we want to determine this equivalent resistance of whole circuit, or in other words, of the battery of resistors connected in parallel. So that's why we can write that delta V over R equivalent is equal to delta V1 over, we can skip this index 1 because they are equal to each other, so it will be delta V over R1 plus delta V over R2. So these guys can be cancelled out because they're the same, and from here we get expression for the equivalent resistance of this circuit, and that will be 1 over R1 plus 1 over R2. So that is the way how we determine equivalent resistance of 2 or more. You can add here as many as necessary resistors connected in parallel. And now I would like to ask you if you found any differences with the ways how we determine equivalent resistance and equivalent capacitance. So they are quite similar, but there is something different.
Vice versa.
Vice versa. For parallel capacitance connection, we used just adding, and for connecting capacitors in series, we got this 1 over C1 plus 1 over C2. So let's say if we have series connection of resistors, the total resistance is equal to the sum of resistors, magnitudes of resistors. If we have series connection of capacitors, the total resistance, the total capacitance of the battery will be smaller than the smallest capacitance of the each component in the battery, and vice versa for parallel connection. So we also need to discuss here two Kirchhoff's laws, which are very handy when we deal with electric circuits. So both DC and AC, because these Kirchhoff's laws concepts, they are applicable to any type of electric circuits. So first one is so-called junction rule, and it tells us that the sum of electric currents which are going into a single junction or some single point of electric circuit should be equal to the sum of electric currents which are going out from them. So that comes from the conservation of electric charge. It doesn't go anywhere, doesn't appear from anywhere, doesn't go anywhere. So the amount of electric charge carriers per unit time which are coming to the junction, that should be equal to the same amount of charge carriers which are coming out from this junction. So in this case, we can show, for instance, this is our junction, like some point at electric circuit, and this is current I1, this is current I2, and this is current I3. So we consider those which are going into the junction as positive, those which are coming out from the junction as negative, and it will be the formulation of the junction rule will be the following: the sum for given junction for all currents is equal to 0. What it means that here on this particular example, we will have I1 as positive minus I2 minus I3, and that is equal to 0. So that is quite straightforward junction rule. And there is another Kirchhoff's rule, which is very important, that is loop rule. So what it tells us, for every closed loop in electric circuit, the gain of potential energy should be, for charge carriers, should be equal to dissipation of energy by these charge carriers. So it means when it comes back to the initial point, so we made the closed loop, the change of potential energy is equal to 0. And that also, in terms of potential difference, we can say that for closed loop, potential difference is equal to 0. So we can formulate it as sum for closed loop delta V is equal to 0. So where it comes from? That's actually conservation of energy. As we discussed at the beginning of this lecture, there are parts of electric circuit which performs work on electric charges and increase their potential energy. And there are parts of electric circuit where these charge carriers dissipate, gain energy while they are flowing through them. So if we have a closed loop, then the change of potential energy or change like potential difference for such closed loop eventually should be equal to 0. So let us consider some example so you have understanding how these Kirchhoff's rules can be applied. There are some features which you need to consider. So let me go to another slide here. We have a bit more complicated electric circuit in this example, and that's why we need to apply Kirchhoff's rules in order to understand what's going on here. This will be A point B C D. Here will be epsilon 1, here epsilon 2, R1, R2, and R3. So here we will have I2, here will be I3, and here will be I1. So this is our electric circuit, which consists of two batteries, epsilon 1 with electromotive force epsilon 1, epsilon 2, and three resistors, R1, R2, R3. So let's say that electromotive forces and magnitudes of resistors are given, and we need to determine the magnitudes of electric currents in each part of this electric circuit. Means we need to determine I1, I2, and I3. For that purpose, we need to apply Kirchhoff's rules. So first of all, for instance, let us consider this junction C, and for this junction C, let's consider the junction rule. So in this case, we can write that I1 is equal to I2 plus I3. So that is our first linear equation, which we get. But as you see, we have three unknown parameters, all our currents. So we need system of three linear equations. So in order to get them, let us consider loop rule, and let us apply it first to loop A, B, C, D. And when you apply loop rules, you need to define the path. So it's either clockwise or counterclockwise. Doesn't matter which path you choose, whatever is more convenient for you in terms of electric circuit, but you need to be consistent and consider within this loop all contributions to potential differences with respect to this path which you choose. So here let us choose path for the big loop, so it's like will be A, B, C, D clockwise. So now everything what is in the direction electromotive force and current in the direction of our path, that will be considered as positive potential difference. Everything what is in opposite direction to the chosen path will be considered as negative potential difference. So in this case, let's check first electromotive force. We see that electromotive force is so plus minus, so it's in the direction of the chosen path. So it will be epsilon 1 minus epsilon 2, because within this loop they are faced against each other. So if we choose clockwise direction as positive, then epsilon 1 is positive, epsilon 2 will be negative, plus minus. And that should be equal to potential difference, also sum of potential differences over resistors. So what do we have here? Current I3 is flowing in the along the path, so it's considered potential difference over R3 resistor will be considered as positive. So we consider I3 times R3, and then we see this current I2 flows in the opposite direction from the chosen positive path. So that will be negative. So it will be I2 times R2. So we have epsilon 1 minus epsilon 2 is equal to I3 times R3 minus I2 times R2. So that is loop ABCD. Now, if we add one more component, we can create another loop and apply loop rule again in order to get one more linear equation to our system. So in this case, let us consider A, C, D loop. So this triangular. And within this, let us assume that our path is counterclockwise. So then what do we have? We have positive electromotive force, E2. Then we have it's equal to two also positive contributions of R2 times I2 and I1 times R1. So I1 I1 times R1 plus I2 times R2. So now we have a system of three linear equations and we have three unknowns. So we can consider I1 as, for instance, like X, I2 as Y, and I3 as Z. Once we have magnitudes of epsilon 1, epsilon 2, R1, R2, and R3, we can solve this system of linear equations and get unknown currents in each components of this electric circuit. So that's a general approach how you apply Kirchhoff's rules, the junction and loop rule, in order to understand what's going on in terms of electric currents in the circuit. Obviously, if, for instance, initially electric, like magnitudes of electric currents are given and some other parameters are unknown, then you consider them as unknown parameters and solve linear system of linear equations with respect to that. So let us summarize this section. We introduce DC electric circuits. DC stands for direct current, means that the direction of current doesn't change over time. Its magnitude may change, but direction doesn't. And in the scope of this DC circuits, we introduce batteries with electromotive force, the internal voltage, and internal resistance, which highlights the fact that batteries are not ideal and there is some voltage drop over internal resistance. So voltage potential difference at the terminals of the battery will be different. In the working electric circuit, then internal electromotive force. And we also have shown that in order to get maximum electric power dissipation over load resistor, its magnitude should be equal to magnitude of internal resistance of the battery. We considered how to calculate the equivalent resistance of resistors connected in series and in parallel. And finally, we introduce two Kirchhoff's rules, which actually can be applied to both DC and AC electric circuit. In particular, first one is junction, and rule, and another one is the loop rule. So at this point, we will finish our discussion for today, and next time we will shortly try to introduce RC circuits in order to show some features of DC electric circuits with time-dependent magnitude of electric current. But that will be already next time on Wednesday. Then have a good evening and see you on Wednesday.